Okay, in this section here in calculus, we're talking about limits, and we're solving limits numerically. But let's say we're given a function f of x, 4 minus square root of x over x minus 16, and let's say that I want to evaluate it when x is 16. So I take 16, I plug it in for x, and we end up getting 0 over 0. So this down here is actually a graph of our function f of x, and here's 16 on the x-axis, and we go down, and I've got a red dot here where we would say there's a y value associated with 16. However, we're getting it's undefined here, and what that means is there's a hole in the graph. So there's a hole right here where this red dot is located. But we've got this concept called the limit, and the limit's going to actually tell us where this hole actually is. So if I were to pick a number that's just slightly larger than 16, like 16.1, and go down, there would be a y value associated with it. If I plug 16.1 into this right here, we would get actually some number out. And if I went to the left of 16, like 15.99 for example, and plugged that in, 15.99 into here, we would also get that some number out, and that number would be close to whatever 16.1 was. It would it would be fairly close to each other. And I'm using this word close kind of loosely. But we're going to use the limit to actually tell where this actually is, this hole is. Except in this section, this is all about doing it numerically. And let's scroll on down and take a look at what I mean by that. Okay, so this is our setup right here. And I'm claiming that it's equal to -1/8. That's where the hole is actually at. But remember, when we actually evaluated and took 16 and plugged it directly into the function, we get 0 over 0. So we've got to figure out where is the hole. And I'm claiming this is equal to -1 over 8. Now what we're going to do here is we're going to do this what's called numerically. And I'm going to pick a number, for example, we'll come way out here to 16.1. We take 16.1 and we plug it into the function here, plugging this in, and you should get -0.12481. Now we're going to get a little closer to 16 from the right hand side, and when we plug 16.01 into our function here, right, we end up getting -0.12498. So you should try plugging this into a calculator, right, and seeing what you get, and you should get something like this. Now I think I do some rounding here. I mean, we can only go out so far, right, and I think I'm rounding to 5 decimal places. But as you can see here, coming in from the right hand side, we're getting close to this exact value here, which is the -1 over 8, but I write it in decimal form here, -0.125. Okay, so you can see here that this number is getting closer to the 0.125. Now I could have done another one, and that's 16.001, and you would see that we would be converging closer and closer to this 0.125, but I just went to 0.01. Now that's coming in from the right hand side, and coming in from the left hand side, so I'm out here at 15.9, plug that in, okay, and we get -0.12520, and then we get a little bit closer to 16 from the right hand side. I'm sorry, we're coming in from the left hand side of 16, and we plug 15.99 in for x, and we get -0.12502. Now as you can see here, that this means that we're getting closer to this 0.125. Now I could have went 15.999, right, and it would just be showing us that we're getting closer and closer to the 0.125. Okay, so that's the difference between evaluating the limit and evaluating the function at the point. We are solving limits numerically. We've got the function f of x is equal to sine x over x. If we evaluate this function at 0, you can see here that we get 0 over 0. And so to actually find out what this value actually would be really close to, we use the concept of the limit. Let's take a look at the graph. Okay, so here's the function sine x over x. Got it graphed out, nice pretty graph here. And when we plug 0 in for x, we're getting a hole in the graph up here where the red dot's located, and it looks like that this hole is located at 1. But to find out where this hole actually is, we can use the concept of the limit, and we're going to look at this numerically. And so what we're going to do here is I'm going to take point 1, plug that actually into the function, so sine of 0.1 over 0.1 gives us approximately 0.99833. And then we get a little bit closer to 0, right, coming in from the right here of 0. We take 0.01, plug that into our function, so sine of 0.01 over 0.01 gives us approximately 0.9998. Now, as you can see here, that I'm getting closer and closer to 1, right, as my x gets closer and closer to 0. Now, we can I could have done 0.001 and plugged it in, and you would have seen that we'd have got we'd be getting even closer and closer to 1. But I just stopped at 0.01. Now, coming in from the left-hand side, we take a negative 0.1 and we plug it in, and we get 0.99833. And we get a little closer to 0 coming in from the left at negative 0.01, right, and plugging that in, and you can see that we get even closer to 1. So you can see then we can probably make the assumption here that as we get closer and closer to 0 coming in from the left, right, our f of x is getting closer and closer to 1. And so therefore we can say that our limit as x approaches 0 is equal to 1. Now remember, this x approaches 0 means we're coming in from the left-hand side and we're coming in from the right-hand side. And if both of these values here are approaching, well, in this particular case happens to be 1, then we can say that our limit is equal to 1. So this is just a numerical way of looking at the limit. Now this particular one right here is we're going to definitely solve quite a few problems using this fact right here, that the limit of sine x over x as x approaches 0 is equal to 1. Now we're going to be looking at this one here. We got our function f of x equal to the absolute value of x over x, and if we evaluated this at 0, we just end up getting 0 over 0. Now looking at the graph of this function, see, so here's our 0 on the x-axis, and if we come in from the right-hand side, you can see then that it's a constant 1, and when we come in from the left-hand side, we can see that it's negative 1. Of course, by showing this numerically, right, so I plug 0.1 in, and 0.1, absolute value 0.1 over 0.1 is just 1, right, 0.01 over 0.01, right, you just get 1. But you notice I've got D and E here. This means it does not exist, and we're talking about the limit here does not exist. But coming in from the right hand side we get 1, but coming in, as you can see here, from the left hand side we get negative 1. So both of these are totally different, and that means that this limit as x approaches 0 does not exist. These must be the same for this to exist. Now if we were looking at what's called left-hand limits and right-hand limits, Okay, we are solving limits, and we're doing it numerically. This function here, which involves an exponential function, e to the 2x minus 1 over e to the x minus 1, let's say we wanted to evaluate this function at 0. So we would plug 0 in, and we end up getting 0 over 0, which is undefined, at 0. And we'd like to probably know what would at least this be close to, right? Let's take a look at the graph. Okay, so here's the graph of the function e to the 2x minus 1 over e to the x minus 1, and we were plugging 0 directly into the function, and we were getting 0 over 0, which means that there's a hole right here in the graph. As you can see here, I've got it indicated, and we would at least like to know where is this hole located on the y-axis. And of course, if we take the limit of this function as x goes to 0, we can find out where that hole is actually located. So that's kind of the power of the limit. And we're going to actually do this numerically. We're going to pick some numbers to the left of 0 and see what their corresponding y value is. And then I'm going to get a little bit closer to 0 coming in from the left, and we're going to get a better approximation of what the y value is of where that hole is located. And then we're going to come in from the right hand side and do the same thing. Let's take a look at this table. So let's look at coming in from the right hand side. So I pick 0.1 and I plug it into the function here. 2 times 0.1 e to the 2.1 minus 1 over e to the 0.1 minus 1, and I plug that into a calculator, and I think I rounded to like 5 decimal places here or something like that, and I get to 2.10517. Now we're going to get a little bit closer to 0 coming in from the right hand side, and I plug 0.01 in, and I end up getting 2.010005. So you can see here as I get closer and closer to 0 coming in from the right hand side, I'm getting closer and closer to this number here 2. And then we do this coming in from the left hand side, so I'm going to go out and pick a negative 0.1 and plug it in and plug it into here, right? And we get 1.90484. And I may have done some rounding here, chopped it off, but and then I get closer to 0 by plugging negative 0.01 in, and I get 1.9005. And so as you can see here, coming in from the left hand side, I'm getting closer to 2, and coming in from the right hand side, I'm getting closer to 2. Now if you really wanted to get as close as you possibly can to 2, maybe, I can't really say as close as you possibly can, but a whole lot closer, you could type in 0.0000001 right into here, or I should say negative 0.0000001 into here, and we'd get even a better approximation showing that we're getting closer and closer to 2, but I just stopped at 0.01. Now we came in from the left hand side, and the way to express this as a limit, I've got a little negative sign right here. You can see the 0 with a little negative sign up here. So we're taking the limit as x approaches 0, right? And this negative means that we're coming in from this side. Okay, we're coming in from the negative side. And you can see this is called a left-handed limit, also known as a one-sided limit. Right, so we're coming in from the left, and we can say that it is approaching 2. Right, and this plus sign means that we're just coming in from the right-handed side, and the limit is also equal to 2. And if both of these numbers here are the same, then we can say then the limit as x approaches 0 is equal to 2. However, if these two numbers here are different, okay, then this limit does not exist up here. Limit does not exist. So this down here is known as one-sided limits. So we're going to actually show, as evaluating limits numerically, how to actually get this number without having to do this. However, if you forget how to calculate limits, you can always do it numerically, and at least you can approximate it and kind of pretty much guess, get a good guesstimation of what the limit's going to. So anyway, okay.